the stream going. So first order of business, talking about homework and formative assessment number 2. So I finished grading all of your homeworks and I entered the grades into the homework portal. And I was so excited to have finished that task, I just realized I didn't give them back to you. So that will be my first order of business upon finishing class is to post them. I will let you know when they're posted. They will be available for download inside the homework portal. So when you log in, you'll see the list of the homeworks that are inside the homework portal, which is going to be 0, 2, and eventually 4, and you'll have a link to your Word document that has my feedback in it. And that is why I had asked you to name your files in the way that I had, which all of you did. Thank you very much for that, because the links are generated automatically within the system using your name. So that way I have a uniform way of naming the files that the system can understand. If you are unable to download them, please let me know and I will be happy to send it to you manually or correct the problem so that you can see my feedback. Those are due if you want to revise it. If you didn't get all of your points and you want to be able to revise it to get all of your points back, those are going to be due on the 12th. So you've got a couple weeks. And if you are planning on doing a revision, please leave my original comments that I gave you and use track changes to show me what you changed. That way I can see exactly what I asked you to do and what you did in response. And occasionally in doing homework, I'll realize that I forgot to check for something, and I don't want to penalize you on the second time through if I realize that I forgot. So leave the comments in so that I can see what I asked, and then I can easily grade your new contributions. So those will be coming back after class. My apologies for forgetting that last step. But on the whole, everything went fine. I did ask for some clarifications for some of you, and I also took the opportunity to weigh in on your plans for using your own data. So if after getting back my feedback, you're still not sure what you're going to be doing for homework 3, please let me know and I'll be happy to chat with you about that. So we have then, gesturing at my other monitor here, our second formative assessment to go over. And I started looking at these, but I haven't gotten through all of them since there's 25 of you. So I will be doing that after class as well. But it looks like for the ones that I've seen so far, it went very well. First question, 3 kinds of indicators, parameters in CFA. So there's 3 in a measurement model. Each item gets an intercept. Each item gets a factor loading. Each item gets a residual. In terms of what those mean, each item gets an intercept. Some of you told me that the intercept is the item's mean. That is not technically correct. The intercept is the item's mean if you choose to identify your model such that your latent factor the indicator is measuring has a mean of 0. That idea that the intercept is the mean is only true in that instance. More generally, the item's intercept is the expected item response for a factor score of 0. So 0 is the key in that. It depends on where you put your 0. If 0 is the mean, the indicator's intercept is the mean. If 0 means something else, then the intercept is the expected value at 0, wherever that something else is. Slopes, the loading, indicated by lambda, that's the change in the item's response per unit change in x, which is the factor. So the increase in the item response per additional, say, standard deviation of the factor, if your factor is identified such that it's mean 0, variance 1. Otherwise, you have to know what a unit of your factor is in order to interpret the factor loading as the change in y for a unit change in x. And residual is the same definition as usual. It's how far off your predicted item response is from the real one. So it's the idea that the model isn't perfect and capturing the variability that's left over after taking into account prediction by the factor. So each item has its own intercept, its own loading, and its own variance for the errors in most cases. There are certain instances in which you might not want each item to have their own of something, and you might have constraints, for instance, across the loadings. We'll get into some examples of that probably later this week or maybe next week. So any questions on number 1? So mu is the intercept, lambda is the loading, and E we'll say is the error term. Good with that? Those ones? All right. One additional parameter that we haven't talked about that you may see in a measurement model is an error covariance. And those are just exactly what they sound like. It's an additional relationship that is allowed specifically between the errors that is reflective of unaccounted for multidimensionality. So your items have something else in common besides the trait. That's what an error covariance would indicate, and it's a way of improving model fit to add them. So those are coming up this week as well. All right, second question. What kind of structural parameters? Which ones need to have a scale? So structural parameters are factor things. Each factor needs to have a mean. Each factor needs to have a variance, and if there's more than one factor, you have to decide whether or not they have an estimated covariance between them. And the factor having a mean is something that you have to put on it. So you can either fix the mean to 0, or you can fix an item's intercept to 0 such that the factor mean becomes that item's mean. Likewise, a factor variance is something that you have to fix to put the scale onto it. Setting the variance equal to 1 for the factor is one way to do that. Otherwise, you can set an item's loading to 1, in which case the factor variance is estimated as the amount of that item's variance that is due to the factor. So the good part of the factor for that item goes up to become the factor variance in that case. Covariances, that's not something you have to worry about identification. Once your variables have means and variances, your traits have means and variances, I should say, then the covariances can be estimated directly from the data, or you can force them to be 0 if you need to for definition of what the factors mean. So certain types of factors are supposed to be unrelated to other factors, such as in when you have method factors or bifactor models. So we'll see examples of that later in the semester as well. So any questions on number 2? Okay. Number 3, identification. So degrees of freedom. How many pieces of data do you have, and how many parameters are you trying to estimate out of them? The idea is that you can't estimate more parameters than you have pieces of data. So the 3 situations: under-identified, just identified, over-identified. Under-identified means you are trying to estimate more parameters than is possible given the data, and you can't do it. So you just get an error that says your model is unidentified and you don't get a full set of results. So that can happen, for instance, if you only have 2 indicators for a latent factor. If you only have 2 indicators, then you only have 1 covariance between them, and that means you can only have 1 factor loading. If you try to estimate 2 factor loadings for the 1 covariance, then you are under-identified, and it's not going to work. If you were to constrain those 2 factor loadings to be equal to each other, then your 1 covariance is exactly mimicked by that 1 loading, and you're at just identified. So just identified means that you have no degrees of freedom left over. Your model is going to perfectly recreate the pattern of covariance. So you have 3 indicators, which means you have 3 covariances, which means you can have each 3 loadings, and it's even. So generally speaking, what you have to pay attention to with respect to identification is covariances versus loadings. That's because each item has a mean going in that is going to be perfectly recreated by the intercept coming back out as the model parameter. Likewise, each item has a variance going in that's going to be perfectly recreated by the item's error variance coming back out. So those are even. The question is how many covariances between your items and how many loadings are you specifying to be able to predict what those covariances are, to capture what that pattern of covariance is. So if you only have 2 indicators, that's 1 covariance. All you can have is 1 loading. If you have 3 indicators, that's 3 covariances, which means you can have 3 loadings, and you're even, you're just identified. Over-identified is when you have degrees of freedom to spare. When there are more covariances than there are loadings being estimated with which to capture them. So if I have 4 indicators, that's 6 covariances. I can estimate 4 loadings to capture those 6 covariances and have 2 degrees of freedom left over. Okay, so over-identified is what we want to be, to have the model be testable, to have some basis for saying the way that we think these covariances are based on our loading matches what's happening in the data, where matches is the goal. Okay. Questions on any of that? So if you're planning a study then, from the perspective of identification, how many indicators do you want to have at a minimum per trait? 4 to be testable and identified, right? But what if one of your indicators sucks? If you're developing a new measure, that's entirely possible. So I'd say maybe 5, because that way that gives you room to get rid of one and still have a testable model. But do you think 5 indicators is going to be enough from the perspective of reliability? Maybe not. Not unless they're really, really good. So these concerns about identification and how many indicators is enough to be able to test whether or not your dimensionality of your trait is consistent with the data is a separate set of considerations for whether or not you've measured that trait well. Just because your model is testable does not mean you've measured the trait well. It just means that you can have a trait in the first place. Alrighty. So any questions before we change gears? Chat window, blowing up without without me watching it. Let me get caught up here. Okay, I haven't, 5, yes, all right, I'm caught up, good to know. All right, so what were we talking about last time? Here, we'll look at the beach while you jog your memories. Maximum Likelihood's theme song, right?
Do you want us to actually answer?
Yeah.
SEM estimation and stata was the last slide that we were on.
Say that again?
The SEM estimation and stata.
Mm-hmm. And I was saying why I'm not giving you Stata examples because there's no estimator in Stata that allows both missing data and robust estimation at the same time. But we're talking about estimation more generally, and the process of estimation is finding model parameters that make your data as tall as it can be. That's the goal. Scaling factor, Alfonso says. What about a scaling factor? What does that refer to?
I'm not sure. I just remember the word.
Okay, that's fair enough. That's why we do reviews, because I don't expect you to remember absolutely everything that was said. A scaling factor is an index of deviation from multivariate normality. So when you have robust estimation, let me pull up a slide that goes with this idea. Slide 41 is where I can find that. A byproduct of estimation with robust maximum likelihood is that in addition to the height of your data that you will get, the log likelihood, you will get something called a scaling factor, where 1 means that your data actually do conform to multivariate normality, and values different than 1 means that it's not. Usually it's greater than 1, meaning that you have excess kurtosis. And that scaling factor is used to provide corrections to the test statistics that go along with model fit that we're going to talk about today, as well as to the standard errors of the parameters in the model. So if you were to run the same model with what I call regular flavor maximum likelihood and robust maximum likelihood, you would get the exact same estimates. Your factor loadings, intercepts, residual variances, any estimated factor variances and covariances, all those numbers would be exactly the same. It's the next column over the standard errors that would differ as a function of the correction, with more of a difference for scaling factors that are more different than 1. Usually positive, but it can go the other way as well. And the derivation of where that comes from is explained in the Ender's Missing Data book in Chapter 5, which I gave you guys on your reading list. He does a much better job of explaining it than I could ever hope to do. All right. Questions about the normality part, by the way. So in regression, like regular flavor linear regression with observed variables, is it the case that your outcomes have to be normally distributed? Do outcomes have to be normal in order to use a regression model to predict them? Or an analysis of variance for that matter? General linear model. Do the outcomes have to be normal? We're talking marginal versus conditional distributions. We have a response, no. That is correct. So in order to use a regular flavor general linear model, a linear regression or analysis of variance, it's not the outcomes that have to be normal, it's the residuals that are supposed to be normal. The conditional distribution given the model predictors is supposed to be a normal distribution. And the same is true for CFA. The models that we're talking about are using a multivariate normal distribution to characterize the data. And so that means that if I have each item as a function of a normally distributed factor, that means the error has to be normally distributed as well. But unlike regular flavor regression, there's no way really to test that. I don't have residuals that I can easily compute from the model because I don't have traits. They're imaginary, they're latent. I could make a predicted trait value for each person, but that is an estimate that has error to it. It's not the same as a y-hat predicted model from a linear predictor of observed variable predictors. So in this one case, it does translate to the data have to be multivariate normal, not just the residuals, because the only thing that's different between the data and the residuals is the factor, and the factor is supposed to be normal too. So if your data are not multivariate normal, then one potential solution to offer some protection against deviations from normality is to switch to a robust estimator. And if you're dealing with a situation where normality actually holds, then the scaling factor that differentiates robust from regular maximum likelihood goes to 1, and the result becomes just the maximum likelihood result. So the worst that it could be is overkill that results in the same thing as regular flavor maximum likelihood. The assumption that we're operating under with respect to missing items is what's known as missing at random. Do you guys know that term yet? Some of you maybe. That sound familiar? Not yet? Okay. So there are 3 kinds of missing data according to social scientists in the world. There's a classification system, and it goes missing completely at random, missing at random, missing not at random. Completely at random is exactly what it sounds like. If you have somebody who didn't answer one of your items, it has nothing to do with what they would have said or what they said on the other items. Like if you're giving out a questionnaire and the copy machine ate one of the pages, and so somebody couldn't answer those questions, right? That's missing completely at random. Any type of analysis that operates on a summary of the data assumes missing completely at random because it doesn't know what happened in building that summary. So for instance, if you take the mean across items as a way of handling missing data rather than the sum, that's functionally assuming missing completely at random. Missing at random is the next one. And this is what the maximum likelihood procedures all are operating as if it's true. Missing at random means it's not random, but it's conditionally random. The item responses are random once you factor in what data you do have about a person. So if somebody skipped question 10, then questions 10's response is random once I factor in what they said for questions 1 through 9. So it's not completely random, it's predictable. Missing at random is reviewer 3's one of their favorite things to complain about because missing at random is not a testable assumption. You're lacking the data to test it by definition. Whether or not there's a pattern to your missing data, you don't know. The third one is missing not at random, and that's exactly what it sounds like. There's a reason for the missingness, and you have no idea what it is. And everything you do is going to be some shade of wrong. So when I say that handling missing data, regular flavor maximum likelihood is the full information maximum likelihood. That means it's using all the original data with an assumption of missing at random. So the height that you would get from someone's data, the shape of that multidimensional height would be the same if they had complete data or if they were missing some. Basically, including additional information wouldn't change the shape of the height, is the way to think about it. For CFA models, if you calculate a covariance matrix for your data and do the factor analysis on that, you will get the exact same answers as if you do full information maximum likelihood, where each person's data go into the likelihood instead. If there's complete data, those things work out to be the same. It's only if there's incomplete data where there's potential for a discrepancy, and any analysis that's built on a summary, like if you have a covariance matrix first, that covariance matrix is missing completely at random as an assumption. It doesn't know how the covariance matrix got built. If you're going with the individual data likelihoods, then it does. So the what program can be used is not so much what program is important, but what is it doing with respect to changing the standard errors and fit statistics to accommodate violations for multivariate normality, and what is the assumption behind any missing data mechanism that's at play here. What Stata does is either, but not both at the same time. M+ has both at the same time, and I'm not sure what Levon does. Does anyone know off the top of their head? I want to say that it's analogous to M+, that they have the same MLR estimator. I'm pretty sure that's the case, but I'm not 100% certain because I'm not an R user. All right, what else do you remember? Anything? Another thing, by the way, that while I'm talking about CFA and assumptions of the model that came up, several of you reported in your articles that people did CFA, but they used WLSMV as an estimator. That is not a CFA model anymore. That is an ordinal factor model that's the same thing as item response theory or item factor analysis. So the way that people describe these things is somewhat inconsistent, and that's why it's important when you write your results sections to describe the model that you're using and what parameters are in the model. So if somebody says, I'm doing a confirmatory factor analysis, but then they go off and start talking about thresholds, for instance, instead of intercepts, I'll know that it's an ordinal model and not a linear model. So the differences we'll get into later on. For now, we are talking about straight up CFA. All the responses are supposed to be normal, a linear effect of the factor in predicting the responses, and any deviations from multivariate normality that are accommodated by having this robust maximum likelihood don't solve the problem that it's still fundamentally a linear model. And if you have an item response that's bounded, such as it can't go past 5 on a 5-point scale, then a linear model is going to be an approximation at best, and it may not work at all at worst. So robust maximum likelihood does not save you from needing a different model in the case of ordinal data. All right, that's what I remember. Other things I wanted to say after reading your homeworks. All right, you ready to talk about model fit? Yes, thank you for that enthusiasm. How do you know if your model's any good? It's a back-asswards way of looking at it relative to what you're used to, because you are going to be praying that you retain the null hypothesis. How is that for crazy? You spent this whole statistics life saying, reject the null, reject. No, you want to retain. Or you want to do not reject if you're from that school of thought that says you can't say retain. So that's where we're headed, back-asswards model fit evaluation. So picking up on slide 43 in lecture 4 here. So just to review, what are we fitting? Here's my CFA linear model equation. The response for each item for each subject is a function of each item's intercept, my lambda factor loading for each item, factor score for each subject, and an item and subject specific error term. So long as each item gets its own intercept, the item means are going to be perfectly captured. So long as each item gets its own error term, a separately estimated error variance for that item, the amount of variability in the item that is due to not the factor, the total variance is going to be fine too, because the total variance is put back together again of however much is due to the factor, which is the loading squared times the variance of the factor, and then whatever needs to be left to make it work back to what the variance is supposed to be becomes error. So error just plugs the hole between what variance is in the item to begin with that we know and how much the model says is there due to the factor. Error just swoops in and finishes it off so that the item's variance is perfectly captured. So long as each item gets its own intercept and its own error variance, the item means and the item variances are going to be perfectly captured. They're not going to be a reason for misfit. So what's left is the covariances between the items and how well they are captured by the loadings, the slopes that relate the traits to the indicators. So that's what we're focusing on. So in trying to describe model fit, there are two very important baselines that your indices of fit, of how well your model matches your data, how well that those two things match. The rest of the indices are going to be relative to one of these two benchmarks. So the one on the right here is the data. That's the one that we've talked about last time, the saturated model. This is just what is the variance of each of the indicators. So if I have 6 indicators here, for example, and what is the observed covariance? This is not a model. It is the data. It will, if you have complete data, it will perfectly match a covariance matrix that you could get out of ProcCore or just any simple descriptive statistic. The only potential difference would be whether the variances and covariances are estimated using n-1 for the sample versus n. In maximum likelihood, it's just n, but you can change that as an option in certain packages. If you have incomplete data, then the covariance matrix that is here as the saturated model is whatever it's supposed to be if the data were complete. So it's adjusting for the missing data in the sense that it's missing at random, not missing completely at random. But this is the right answer. So this saturated model slash unstructured model, it's going to be called H1 in your output. This is as tall as the data can be. If you let each parameter be whatever it wants, you spend all your degrees of freedom. You're not trying to predict anything. You're just saying, what is the variance and covariance pattern in the data? This is it. Our objective is to get as close to this as possible, but spend fewer degrees of freedom than is possible. So our model, which is going to be called HO, the null hypothesis, is going to be hopefully somewhere on this continuum of best to worst. And we want it to be as close to best as possible. Worst is over here. Worst is known as the independence model or the null model. And this is letting each item have its own intercept, letting each item have its own variance, but saying there's no covariance whatsoever. So this model would say there's nothing worth modeling. You don't even need your factor because these items aren't even correlated in the first place. So our model is going to be compared in two different ways to these benchmarks. Relative to the null model, how much better did we do? The null model says there's no relationship, and we're saying, nuh-uh, the relationship is like this. How much better did we do than the worst? But then relative to the best, are we close to the best? Relative to the best, how much worse are we? We want to be as close to the best as possible, as close to saturated as possible. And so the different fit statistics that you are given as part of your output differ in whether they use the worst as the comparison, in which you want to be as high as possible relative to worst, or whether they use best as comparison, in which you want to be as close as possible. So the heights are given to you first. This is example M plus output. We're going to look at this for our um, forgiveness of situation 6-factor example in just a moment. It's giving you log likelihood for HO and H1. And for many, many years, even me, when I would teach this, would get these confused because these are arbitrary labels. And I'd be like, okay, which one is mine? And one day I had a question in office hours that will forever prevent me from getting these confused. So can I tell you a quick story? Okay, so back when I used to teach at the University of Nebraska and there was no pandemic and we actually like sat in a room together and didn't worry about breathing on each other and shit, I used to have my office hours in a computer lab, and people from both classes would just come to office hours and sit there and work on homework, and I would float around and answer questions. Well, there was one day where there was like 20 people in there, and so I'm floating back and forth across people answering questions, and one person, her name was Lindsay, she looks up and she says, "Am I the hoe?" I said, "What?" She's like, "Am I the hoe in M plus?" I'm like, "Oh, you mean are you the HO model?" Yes, Lindsay, you are the hoe. And so I will tell all of you, you are the hoe. You are not the H1, you are the HO. The HO refers to your model, whatever you set it to be. 1 factor, 2 factors. The H1 is the best model it can be. I'm number 1. I'm H1. So you will never forget now, you are the hoe. So the best possible model, the H1 here, has a height of minus 11,322. The reason that this is such a weird number is because this isn't a log scale, but bigger is better. They want to be taller, right? I wish I were a little bit taller. This number, this 11,322 thing, that's as tall as the data can be. So our question is, relative to the tallest it can be, how tall is our model? What is the combined height of the data given our model parameters? How close did we get? And we got to 11,536. Okay, is that close enough? Well, to answer that question, normally we would just take the straight difference between these two and multiply the difference by minus 2. And that difference, when multiplied by minus 2, is distributed as a chi-square. But because of these correction factors, we will have to change the formula to include them, and M+ thoughtfully does this for you already, as does every other SEM package on the planet. So this thing right here, the blue box that's labeled chi-square test of model fit, that is the difference in minus 2 log likelihood rescaled by these scaling factors between your HO model and the best possible H1. It's how far off you are from best. And we are off in this case by about 308 with 9 degrees of freedom. So what does 9 degrees of freedom stand for? That means 9 fewer parameters than all possible. We didn't spend 9 that we could have. And the p-value that goes with that chi-square is 0 to 4 decimal places, meaning in this case, a significant p-value means we reject the null, right? Saturated model is what this is comparing it to. So reject the null in this case is bad. That means our data are significantly shorter than the best possible model. So we have not matched the pattern of covariance in the data with the model that we fitted. That's what this is telling us. Our model is not good enough. It is significantly different. Question from the audience, why is the saturated model the unstructured model? Unstructured is what this model is called in a mixed effects modeling terminology or multi-level models. Unstructured is the type of uh, what it's called in SAS or Stata or SPSS when you have a set of repeated measures and you allow their variances and covariances to be whatever they want in the data. That is called an unstructured matrix. That is exactly the same thing as a saturated model in SEM parlance. Both of those words mean that they just let the data be whatever they want. We're not constraining it to be anything. We're not predicting it. We're just letting it be. And that is as tall as the data can be. And our result here that is significant means our model is significantly worse. Our HO log likelihood is significantly lower, not as tall, not as good. So that's no good for us. One factor does not fit. Otherwise, our model would be close to the tallest, closer. The pink thing down here, this is also called chi-square test, but it's for the baseline model. And this piece of output you can ignore. It has nothing to do with your model. What it's comparing is the null model to the saturated model. In other words, are there any covariances at all in your data? Is there a difference if we let the covariances be whatever they want to be and holding them to zero? And this chi-square on 15 degrees of freedom, which is the number of covariances in the data, being significant means, yeah, there's some covariance here that's not zero. Meh. So that's rarely of interest. So that one we're going to ignore. It's this one that we're going to focus on and all the different ways of expressing our deviation of what our model says the covariances should be relative to what the data say. So you are the hoe. There's your take-home message for that. H1 is the I'm number one. That's as tall as I can be. Can you think of a situation in which the hoe and the H1 would be exactly the same? When would you be as tall as you can be from your model? Just identified. Correct. Yeah. So if you fit a single factor to 3 indicators and you give each indicator their own intercept, loading, and residual variance, then you will have spent all your degrees of freedom, and the hoe is the H1. So it will fit perfectly. You will have just rearranged the data, basically, from 3 covariances into 3 loadings. Good. So here's the questions that we have to go through in evaluating our model. Global fit. On the whole, have we adequately recreated the pattern of covariance across our indicators using our factor loadings and factor covariances? Local fit. Is there any more specific problems? Then we'll look at the parameters and we'll look at reliability and information. How good is the model at measuring individual differences in the trait? So global fit is going to take us a little while to get through. So the thing that we just looked at is known as the chi-square test. Significance is bad. Relative to the perfect model, our HO chosen model, we want it to be as close as possible. So if it's significantly different, that means it fits significantly worse. You may see people use ratio rules like chi-square divided by degrees of freedom needs to be better than 2 or 3. That's not a thing anymore. Don't do that. At least one of you reported that in your as a index of fit. That's not a thing. However, just using that chi-square test is going to be insufficient in many cases because chi-square is going to be inflated in large samples. So a couple of you I noted have like samples of like 13,000 responses. Who has like 13,000 people in their homework? You people? Yeah, Jing does. There's at least a few. Kelly, yep. So you know what? I don't even need you to do your homework. I'm going to tell you your chi-square is going to be significant. It is. Because with 13,000 respondents, you have a shitload of power to find tiny discrepancies between what the data say and what your models say to be significant. People with small samples love to remember this rule. Well, chi-squares depends on sample size. I mean, like, yeah, you have 100 people. This is not your problem, right? You can't always use the rule. But it is almost always the case that chi-square is going to be significant. The question is, how far off are you in more of a practical sense? In other words, we need some kind of like effect size that goes with this idea of just of significantly different than the perfect model. So because of that, we end up with all of these other indices of fit. Some of them are known as absolute fit indices, and those are the ones that are relative to the best model. And others are known as comparative fit, and those are relative to the worst model, the null model. How much better did we do than the worst? How much worse did we do than the best? So two different types of flavors of these things. It used to be the case that there were sort of hard and fast rules accepted for what good was for each of these, and I'm going to give those to you, but with a caveat that more and more research within the last decade or so has suggested that what good is should not be a hard and fast rule and depends on a lot of different characteristics of your model. So I'll give you a sense of that, some flavors of research that are looking at that. It's becoming more of a flexible situation than it ever was before. So I'm going to give you the cutoffs, but just know that there are situations in which they're not going to be as useful. So here's one of them. This is going to be acronymapalooza, by the way. Fun. SRMR stands for Standardized Root Mean Square of Residual. By the way, these names that I'm going to give you, if they have the words residual or error in them, you want them to be small. If they have the name fit in them, you want them to be big. So this one has residual in it. What it is the sum of the discrepancies between what the model says the correlation between items should be and what the data say. So it's like how far off is each of the correlations, add them all up and put them together, and you end up with this thing. And conventionally, values of 0.08 or less would be considered good fit. So on average, your correlations predicted by the model would differ from those found in the data by 0.08 or less. That one shows up on most of your stats packages. Another one that is in a similar fashion, this is a big one. This is very commonly reported. RMSEA, root means, say it properly, root mean squared error of approximation. This one is relative to the saturated model as well. So it's how far off is each element of your variance covariance matrix, and we're focusing on just covariances most of the time, per degree of freedom left over. So built into this is a parsimony adjustment such that the more degrees of freedom left, the happier RMSEA is going to be with you. So more degrees of freedom left is a proxy for models that have more indicators. So all things being equal, if you have, say, a single factor model with 4 indicators, RMSEA is not going to like that as much as a single factor model with 10 indicators. Because with 10 indicators, you've got a lot of degrees of freedom left over. With 4 indicators, you've only got 2. So it corrects for the offnesses between the model predicted covariance matrix and the one in the data per degree of freedom left over. And it ranges from 0 to 1. Since it has the word error in it, we know smaller is better. And people love to put labels on this one. There's like good, adequate, acceptable, mediocre. Just give them the number. Less than 06-ish is sort of the conventional where good is. You get people sort of trying to stretch it into this. That's kind of like people saying like trending, like p equals 0.06 is like approaching significance. People want to put that kind of language into these and say it's close to 0.06. It's just, just a little bit worse. One of the things that's unique about RMSEA is that you can also get a confidence interval around your estimate, and these confidence intervals work just like they do in other areas of statistics. The more people you have, the tighter your interval. So you could end up with, say, an RMSEA of 0.06. In a small sample, the interval could be anywhere from 0 to 0.12. And in a big sample, you could have an interval of 0.05 to 0.07, for instance. And so it's good to report the confidence interval in addition to the point estimate because that is given to you. And the other thing that is given in the context of this is another p-value. This one is testing against an RMSEA of less than or equal to 0.05, and that is known conventionally as a test of close fit. So whether or not your HO model exactly matches the H1 best model is just absolute fit. Whether or not it's close enough, as indicated by an RMSEA of 0.05, is close fit. And so you will see people report the p-value that goes with this too. And just like the one for absolute fit, you want to retain the null. You want to be able to say you have close fit. If you reject the null, you're saying you don't have close fit. It's worse. So those two, SRMR and RMSEA, are both lower is better indices. And question, the degrees of freedom here is people and not items. Nope, it's still items. People are not part of the story because what we're focusing on really is a covariance matrix. It is the case that all of our parameters are going to have tighter intervals around them the more people you have. But in terms of degrees of freedom and parsimony, we're talking about number of variables in this case. Yep. Okay. So the other class of indices are relative to the worst model. So these are comparative fit indices of how much better your HO model is than the worst possible model that has no covariances in it. And so these ones have the word fit in it, which means you want them to be high. So close to 1 is possible. One of them is the CFI, and the other one is either it's called the TLI for old white men who named it after themselves, or the non-normed fit index to reflect the fact that it actually does go below 0 and above 1. Both of these are comparing against the null model, and so you want them to be as much better than the worst model as you can get, which means a value of 0.95-ish as a good fitting model. So it's kind of like you have like 7 different watches, right? It's like, well, it's 12:43. No, it's 12:44. Nope, I think it's 12:39. And you're hoping that they all sort of converge onto what time it is, but there's actually no guarantee that they're going to agree. And I have seen this in practice many times where, say, RMSEA is happy with your model, but CFI is not, or vice versa. And part of the reason is because they're relative to different benchmarks. These ones are relative to the worst possible model that you can have and how much better you're doing than worst, whereas RMSEA and SRMR are relative to best and how much worse you are than best. So they're converging onto hopefully the same point, but from different directions. So back in the day, like I said, there was one simulation study that is largely responsible for all of these values that are on here as what good means. Hugh and Bentler, this one study has been cited over 68,000 times. Like it's basically the Bible for what is good. And what it did is generate fake data and see what proportion of time when you fit the wrong model to it, these statistics actually flagged it as wrong. And then they developed the cutoffs based on that result. Well, no one study can anticipate every possible way that data can vary from each other and models can vary from each other. So for instance, in their study, they opted not to vary the strength of the relationship of the indicators to the traits. They were all relatively high. They fit a model that had only 15 indicators of 3 factors, and so relatively few variables. And they generated data that were perfectly multivariate normal. So they aren't like ordinal data. So all of those recommendations that RMSEA should be less than 0.06, SRMR should be less than 0.08, CFI should be greater than 0.95, and TLI should be greater than 0.95, all of those came out of this one set. And it turns out that things are a little more complicated. So I've added some articles to your reading list that take into account each of these things and sort of dive a little bit deeper that suggest how the standards actually need to be different as a function of these things. So here's one of them, missing data. This article makes a point that in retrospect should have been obvious, but the more missing data you have, the easier it is to get your model to fit. Now think about if you have, say, a pattern of covariance where you got all of the covariances right except for the covariance between item 1 and 2. Let's say your model whiffed on that one. You know how you solve misfit? Don't have item 1 or 2. Problem solved! If you don't have the data to show the misfit, then you end up with a rosy picture of what happened. And so that was one of the conclusions of their study. For instance, if they had a model that had correlated residuals that were ignored. So for instance, they fit a model in which they had a known factor structure, but in reality, there were also additional relationships between the errors of specific indicators that were not part of the model. And if those indicators were missing on a different factor, there was no impact. But if they were missing from the same factor, then the RMSEA value, so the y-axis here is an index of misfit, looks better in the cases where you're missing data. So you could end up with a lower RMSEA, meaning a lower discrepancy between you and the perfect model, if you lack the data that demonstrate that discrepancy. So I'll say that again. You can end up with a measure of fit that is better, an RMSEA that's lower, if you lack the data that would indicate that discrepancy. And so they caution that just because you have good enough fit statistics, if parts of your model that are showing misfit have missing data, then those fit statistics are probably optimistic. And the same thing happens with missing data that follow a pattern as opposed to missing completely at random, as shown on the other side here. So that's one thing to take in mind. Even though all of these algorithms handle missing data, if you're missing the data that is needed to test the model, then the results of that test can be optimistic. Same issue if it's due to structural misspecification and not just correlated residuals. So here we're looking at the size of a factor correlation between two factors. So how do you know if you should have one factor in your model or two? Well, the extent to which you need two factors depends on how correlated they are. If you have two factors that are perfectly correlated, that's the same as having one. To the extent that the factors diverge, that correlation comes off of one and gets lower, you need two factors. And so that's what they're manipulating here. On the x-axis is the strength of the correlation between factors and the percent missingness. And you can see that RMSEA again, which measures misfit, so you want a low value, looks better. It doesn't track the fact that there's misfit as much when there's missing data. So that's one of the articles. Here's another one that looks at whether or not these cutoffs for fit indices should differ as a function of the number of indicators that you have. And this one is actually very tricky to summarize. So this is looking at different sample sizes of 200, 500, and 1,000 versus a population model where they know exactly what's going on. And for instance, this is CFI on the y-axis over here. So CFI is relative to the worst model. So you want it to be more. A CFI of 1 is the best you can do and 0 is the worst. And as a function of the number of indicators, like look at the left column here, correctly specified. That's when they fit the right model. They fit the model that generated the data. The more indicators that you get, so the x-axis is showing 10 indicators, 30 indicators, all the way up to 120, the less well it looks like your model fits according to CFI, even if it's the right model. So if you're in a situation, for instance, where you have 120 indicators, super high reliability, hopefully, it could look like your model totally sucks. A CFI of zero point 0.6 would not be considered good enough by any stretch of the imagination, even if it's the right model. Now, this is in a situation, the other thing that separates these panels is the strength of the factor loadings. So the top panel is factor loadings of 0.4, so a weaker relationship between the trait and the indicators versus factor loadings of 0.8. So the problem starts to go away when you have stronger factor loadings. We see the opposite problem for RMSEA. So if we look at, say, this one here where we've misspecified residuals, in that condition, they fit the factor model, and 2 of the indicators should have had an error covariance, or I don't remember how many, but some of them should have had an error covariance and they left it out. The more indicators that you get, the lower RMSEA is. RMSEA is your model relative to the perfect model, so you want it to be as small as possible. So the more indicators that you have, the happier it is with you, because RMSEA is misfit per degree of freedom left. And if you've got a lot of degrees of freedom left, then that balances it out. So you can end up with a great RMSEA just because you have a shit ton of indicators, even if the model doesn't fit very well. And question is, the reason why they know they have the right model is because they have the data that they can truly compare it to. The reason they know they have the right model is because that's how they generated the data. So in all of these studies, the way that it works is that they generate data that is entirely consistent with a model, and then they fit the right model to it. And that's the benchmark for the best that could happen. And then they deliberately fit the wrong model as comparisons. And what you should see is that if these fit statistics are working like we're supposed to, that when you fit the wrong model, it should fit worse. And so what these slides are showing is that in the conditions where you have the wrong model and it should fit worse, how much worse it's fitting is a function of other stuff that has nothing to do with how much worse. Other stuff like reliability of the variables and number of indicators. So it makes it so that you can't just unilaterally say, oh, a CFI of 0.95 is what you need. Like, well, in this condition, the best you could have is a CFI of 0.6. So you have no shot at saying you have a good model if you have 120 indicators. Now that's pretty rare in practice, but it should give us pause in just unilaterally saying, yes, this is a good model, or no, this is not good enough yet. So another question, do we have to meet both absolute fit and comparative fit when we want to say our model fit is good? Oh, it depends on who your reviewers are. That is the answer. The way that I have phrased these things before is just to simply be honest and say the model fit is acceptable according to CFI, but not according to RMSEA. And that's where art and science start to intersect. And whether or not the things that you could do to make the model fit better would ruin what you're trying to accomplish. So I'm going to show you in a minute Voodoo, maybe not today, maybe next time, Voodoo that will tell you how to fix this. As part of your output, you can ask M+ or Levon to say, hey, how can I fix this and make it better? And it's like, oh, I know. You put a correlated error here, and you put one here, and you put one here, and boom, it fits. But then what you have is not my single factor model of situation forgiveness or whatever. Then you have situation forgiveness and some stuff, because stuff has creeped in via these error correlations. So the things that you would do to improve the model then change the interpretation of the model. So it's like, okay, I want it to fit well, but I don't want it to fit well at the expense of having it make sense and have it be likely to replicate, because these voodoo put this here and put this here are all very sample specific and may not replicate. So I think the question is, like, what's the best that it could be given what is reasonable to do with it? And there are actually newer papers still coming out, one that's under review that I didn't give you that I saw, looking at using simulation for your own data to try and get a sense of what the sampling distributions of these would be and what good would be given a completely customized set of parameters for how many variables you have, how many factors, reliabilities, and that kind of stuff. So it's an ongoing science. But yeah, the reality is that these things may disagree, and there may be situations in which it looks like you have shitty fit, but it's actually not that shitty. And there may be situations in which it looks like you have good fit, but it's not really that good. It's messy. It's messy. That's the reality of it. Here's something that should give you pause. And speaking of messy, this is the impact of reliability. It turns out that if you have shitty indicators, it's really easy to make it look like they fit. So what we're looking at here is a replication of the original Hugh and Bentler design, where they had 15 indicators measuring 3 factors. And rather than have all of the standardized factor loadings in the neighborhood of 0.7, 0.8, so good items, they lowered them. And so they had a condition, for instance, of 0.4 for a standardized loading, 0.7 versus 0.9. And these are the distributions of what happened under each of those conditions for a model that they knew misfit. So what they did was fit a 3-factor model, and they left out one of the factor covariances that was known to be in the data. So like 2 factors were supposed to be correlated like 0.3, and they forced it to be 0. And so if we look at the 0.4 condition, that is the lightest set of bars in each of these pictures. Here's RMSEA. So they know this model is wrong, right? But if the loadings were 0.4, all of the time, and all the replications that they did, the RMSEA that they found would have been called acceptable. For the same level of misspecification, so the same amount of model wrongness relative to what was generated in the data, if they had loadings of 0.7, then it would be considered wrong. And if they had loadings of 0.9, it would definitely be considered wrong. So this means that if you have low reliability, it's really easy to get fit statistics that think that the model's good. If you have low reliability, then that's a signal for low covariances. And so it's a much harder to pin down when a covariance matches or doesn't match if it's not a strong covariance. So low reliability can lead to well-fitting models that don't actually fit that well, as well as a lot more variability. So here, note this is CFI under the condition of low reliability. It could be basically anything. So isn't that depressing? And here's one more. Here's a paper that talks about CFI versus RMSEA, and they have a plot. They figured out mathematically when these things are going to agree versus disagree. And so what you're looking at here on the y-axis is a function of positive values mean that the CFI is going to be happier with your model than the RMSEA, and negative values mean that RMSEA is going to be happier. And the x-axis is the amount of misfit. And so there's actually a function here where they can anticipate, based on the amount of misfit and the amount of degrees of freedom, when these two indices of fit are going to agree versus disagree versus one be happier than the other. Holy shit. So yeah. So misfit used to be simple. It's not anymore. That just means that you may have to make a lot more arguments to reviewers who want to hold you to some standard if you're in a situation where that standard is not going to be possible given your data. this kind of stuff. So it's tricky. If you're in a situation where everything is agreed, then you still can't necessarily be like, yay me, I did it, because that can happen if you have low reliability. So it's messy. It's one of those things where this is where people can choose whatever numbers they like and say that their model fits. So I've kind of lost faith in global fit because of all of this. I'm not necessarily sure that having a number that summarizes your model is necessarily going to say that it's good enough. So that leads us to the next piece, local fit, which is much more important and much more useful. So let me put it to you this way. What is local fit? I know most of you don't have kids yet, right? But pretend you have latent children, right? They're unobserved, right? They might become observed someday or they might not. Who knows? But your latent child comes to you one day with a report card and they have a 3.0 grade point average. Now, what do you say to them? Well, some of you might say, good job, honey. And others might say, okay, well, there's probably some work to do. But in figuring out whether or not we want to be happy with a 3.0 grade point average, right? What we want to know is how that average came to be. Did they get 4 Bs? In which case, like they're doing fine, but maybe they need to work a little harder across the board? Or did they get 3 As and an F? Because either one of those is going to give you a 3.0. And if they got 3 A's and an F, is the F in something important like math or is it like PE, where it's like fine, you don't have to play base soccer if you don't want to, honey. I'm okay with you failing gym. But that difference, whether it's 4 B's or 3 A's and an F, that boils down to an analysis of local fit, looking at how they did in each class and trying to figure out why the overall average came to be what it is. The same thing is true here. All of those numbers that are trying to track how good your model is some kind of average across all of the possible sources of misfit. So if I have 6 items, there's 15 covariances. The model is trying to account for all 15 of those covariances. Did it get 14 right and ruined one of them? Or did it sort of whiff to a little bit on all of them? Trying to figure out why the model doesn't fit is going to be essential in trying to make it fit better, or even if these numbers say you have good enough fit, because that can happen in a lot of instances in which you don't have good fit, checking local fit is going to be essential. So that's the next step, is to do some detective work to figure out why it is that you have the pattern of global fit that you do, and if you can make it better in a reasonable way. That's what we're looking for. So the idea of local fit is going to boil down to residuals. But it's not residuals in the same way that we have like residuals for each item. This is an unfortunate terminology, and it's why I'm trying to say item error variances and save the word residual for this. Residual in the context of fit is mismatch. It is the discrepancy between what the data say the covariances between items should be and what the model says. It's how far off the covariance matrices are. So you will get, as part of your output, a residual matrix. It is a matrix of covariance or correlation discrepancies. And it tells you where the holes are. So the covariance between items 1 and 2 was accounted for, but the covariance between items 1 and 3 was not. Okay, what is it about items 1 and 3, and why is my model not doing that one accurately? And you're going to end up getting diagnostic information standardizing these residual discrepancies into something that looks like a z-score. So these are known as normalized residuals. There's also standardized residuals. We're going to work with normalized in this class. It's how far off divided by the standard error of the covariance itself. And so it works out to be something like a z-score, where values of about 2 or 3-ish would indicate discrepancies that are relatively large. The size of these discrepancies are going to be influenced by sample size. So they become huge in huge samples. So you're still looking for ones that are relatively to the others bigger than what you would see. And if it's a positive residual, then that means that the items are actually more related than what your model said. They have something extra there that you haven't accounted for in their relationship. And a negative means they're less related, like they don't want to be on the same factor after all. And so you can use this information to suggest what an alternative structure might be that fits the data a little bit better. And Kelly says I froze. Am I back? No, Kelly froze. It could be. We all freeze from time to time. So we get to do some detective work to figure out why our model is broken. And even if it doesn't look like it's broken, this same detective work is necessary to make sure that we haven't missed anything because of all the idiosyncrasies of global fit. So that's where we get to practice next time. These classes go so fast. I know you guys probably don't think so because you're sitting there at Zoom and it's like it's endless. But from my perspective, it's like we're done already, but I haven't even gotten to the good part yet. So yeah, we're done already. But before we adjourn, any questions on what we've been talking about so far? All right, then it's Tuesday, which means I don't say have a good weekend. I do say let me know if you need anything. I will let you know when your homeworks are ready for download with my feedback. Office hours start now if anyone wants to chat. Otherwise, take care of yourselves. Come back Thursday. So, bye everybody.